important. And then we will, if we have some time left, I'll go through some additional slides, and we'll make sure we do some hard stuff that will be on the exam. So we always want to have as much material the exam covers as possible, right? So remember, I won't actually be present for the exam. The exam is what, Monday at 10:10? Or is this the 1:10 one? I'll tell you. Exam is, one moment, 10:10, operating system spinal. 10:10 to noon. That sound accurate to everybody? Okay. So Monday, 10:10 a.m. to noon. So I won't be here, but the exam will be here. You have the full 2 hours to take it. I typically design finals to take about an hour. So it should not be a time stressful thing. If you're still writing after 2 hours, chances are you didn't know what you were doing. Okay? So in any case, that's the exam. So about an hour. You have the entire class period. There will be about 10 questions. I like to ask right around 10 questions for exams. Each one will be weighted equally, 10% of your grade per question. There will be no programming. So just like in the 325 class, even though we've done quite a bit of programming stuff in here, this class is not a programming-centric course. We use programming, and like I tell people, programming is in computer science. Programming is to computer science as like a hammer is to a carpenter. It's a tool we use, so we've used it in here to explore aspects of operating systems, but it's not necessarily a topic that's testable for the class. So the questions are going to be short answer essay type questions. There will be no multiple choice. I don't do those. And there will be no like fill in the blank where you have to come up with like the perfect word or something, you know. I want you to prove competence. I'll ask questions. Your answer will be a sentence or two. That type of thing. Okay, so questions about the format of the exam. Okay, so let's go back and go through. It will be cumulative, so it'll cover the entire semester. So let's go back all the way to chapter 1 and go through some of this, and I can tell you what things I deem to be important and which things I think are kind of fluff that you don't really need to worry about too much for the exam, so you can kind of focus your studying. Well, here just in general, well, I'll just go through the individual slides. So obviously you should know what an operating system is. I don't know if I'll ask it as a question, but you know, understand that it's the piece of software that sits between the human and the hardware. The pieces that go into an operating system, certainly kind of understanding that you have a CPU scheduler, a process scheduler, a memory manager, file system manager, those types of things. Kind of what are the components of the operating system and having an understanding of how they all work together. Okay, so similar here, what do operating systems do? So how do those things work together to accomplish those tasks? Certainly the history of operating systems. So what's the difference between an operating system and a distribution? So operating systems are like the 9X kernel or NT or the Linux kernel. These are the core operating systems, but we call, you know, Windows XP was a distribution based on the NT kernel, which is the actual operating system. Okay. History of OSs and kind of the differences. There'll probably be one question dealing with something along the lines of the history of these guys. You know, questions like the difference between Windows 2000 and Windows 98 or something like that. You know, tell me what you know about these things. Could be a question with Apple history. I probably won't take a whole lot of questions about, you know, history stuff. I would say maximum of 2, but probably 1. So all the history stuff will just fall into more than likely 1 question dealing with either the Apple backstory, the Microsoft backstory, or the history of the actual distributions, or even a made-up question that I didn't cover. So any of those would be fair game, I suppose. Okay. OS's. Well, that'd be a decent question about the blue box. Relates to OS X Panther. So first version of OS X. That was the virtualized version of OS 9 because none of the applications worked for OS X yet. So now that I've mentioned it, it probably won't be the question, but possibly. Possibly. Concept of the Bootstrap program, a little piece of software or firmware that goes from computer power up and actually launches the software operating system. Could be a question on USB stuff, kind of like technology competence, especially for our Best Buy employees in here. Of course. Okay, so that crap. The idea of interrupts. Interrupt handling, not important. More the concept of what does it mean to be interrupted. Specifically as we've dealt with it with CPUs. You know, under what circumstances might a CPU be interrupted? You know, it runs out of time. You know, the current process it's working on, or current when it's on the CPU, it's a job. The current job it's working on doesn't have any more allocated time. It's going to get interrupted. Time's up. Or I/O. You know, there's an I/O request going to get interrupted, so it doesn't waste CPU time. So interrupts as far as that's concerned. Not important. Not important. Not important. Certainly the storage stuff from the concept of speed versus cost. You know, that concept that hard drives tend to have the biggest capacity, tend to be the lowest cost, and tend to be the slowest. All the way up to the L1, L2, L3 cache, which tend to be much quicker, significantly smaller capacity, and significantly more expensive per bit or something, you know, however you want to measure their cost. And then even the fastest being, you know, the register sitting directly on the CPU. So the closer you get to the CPU, the faster things are. And as soon as you start introducing actual cables that sit between the memory and the CPU, things slow way down. Make sense? Yeah, if you have it soldered, you know, nearby the CPU, it's going to be pretty fast by human standards. You start having serial ATA cables running to the hard drive, you're going to expect a pretty big slowdown. Okay, so the storage stuff from that perspective. So they kind of show this little pyramid here. Registers being super fast, and your caches, main system memory, electronic disk. I guess that would be more of like a solid state thing today. I'm guessing that's what they're talking about. Magnetic disks would be hard drives. So this is kind of our transition little zone here. Optical disks would be like CDs, DVDs. Do they even make CDs anymore? Yeah. I know you can buy music, but I mean, nobody burns stuff on CDs anymore, do they? Or is it just music? If you have a CD player in your car, you burn a CD to play in your car because it doesn't support DVDs. That's the only use. And then magnetic tapes, which are kind of data backups. You know, so magnetic tapes, you tend to have, you know, huge capacity but very slow. And the idea is to back up a computer on a nightly basis or something like that at a doctor's office, and it takes 7 hours, but who cares? Nobody's there. It's kind of the idea. So the trade-off is almost always capacity to speed and cost. This kind of goes in with that whole argument, the caching stuff. The concept of multiprocessors versus single processors and what that means. Questions like, is two cores always faster than one core? Stuff like that. So understanding the implications of having multiple processors versus a single processor for different types of problems. Certainly threads. The idea of lightweight threads versus heavyweight processes. The idea of a dual core design, specifically as it relates to the caches. Remember, with dual core, we have each core has registers in the L1 and L2 cache associated with it. The L3 cache is used to bridge between cores. Remember that factoid? I can see that guy making an appearance. So, everybody understand what I just said? Sounds like a good question to me. Hint, hint. So, assuming I come up with that same idea when I'm writing the exam, which probably will be today since I'm flying out tomorrow.
Just to double check on that one, is it difference between cores or between separate processors? Like, is the L3 cache on the motherboard?
Yes, it would.
Or in between
the short answer is yes. Whenever you have multiple cores, whether it's across two physical processors or a single processor, the potential exists to have L3 cache. L3 cache is not required. L3 cache is a much more modern approach and probably only relates to multiple cores on a single physical piece of hardware. So it's probably still on that piece of hardware, not on the motherboard. But that isn't to say that you couldn't take the concept of L3 cache and bridge it on the motherboard between two physical processors. That makes sense? So it realistically relates to dual core, not dual processor, but it doesn't have to. But from your perspective, the idea should be that it doesn't belong to an individual core. It's shared across cores, however that is organized. Important. The idea of multi-programming, so this is kind of multitasking. So operating systems that had only had to do a single task at a time. What are the things that go on with that versus, operating systems that need to support multiple programs running simultaneously. And more recently, so remember the first chapter kind of dealt with the high level, here's all the crap about the operating systems at a 2,000-foot view. More recently, we've been looking at process and CPU scheduling at a more detailed level. So this idea of time sharing between jobs running on the CPU, so all of them give the appearance that they're running at the same time. Memory layout, not really important. Well, important, but we didn't cover it in detail, so it's not important for the exam. The difference between user and kernel mode, not so much the transition, but the idea that some programs have a higher priority than other programs, so things that are owned by the operating system would run in kernel mode, so they have protected access to certain aspects of memory where other user-level applications don't. The concept of process management. Then we take that to the more modern thing, the more recent thing we've done where, the process manager has to keep track of all the processes that currently exist, the processes that are currently ready, the processes that are currently waiting. So he's kind of the manager of the current state of the traffic of processes as they move through the system. So things like program counter and stuff like that, things like context switching fall into this category. So under process management, creating and deleting user and system processes certainly included. Suspending and resuming processes, that's the context switching. Providing mechanisms for process synchronization, that's what we've been talking about more recently with the inter-process communication stuff. Process communication is sending messages between them. Synchronization is probably signals. So one guy doesn't do something out of order. So both of these lines are kind of involved with inter-process communication. Mechanisms for deadlock handling we never really discussed. Deadlock is when you have two different processes relying on the same thing and somebody needs to get there first. So we didn't really get to it. So unless we get to it today, that won't be on the exam. But just for trivia knowledge, and I won't, unless we actually physically talk about it or really talk about it today, it won't be on the exam. But kind of the main tool for handling deadlocks is something called a semaphore. It's a special kind of integer that is atomic. So when you need to grab the CPU, or you need to grab a resource, whoever gets there first, when they hit the semaphore, that's an atomic action. So two people can't do it at the same time. They could almost do it at the same time, but one of those two is going to get the resource because of the way a semaphore works. Okay, so it's like two people rushing into the counter at McDonald's. In humans, in real life, we could both start ordering at the same time. In computers, because of semaphores, that can't happen. Okay, so that's kind of our main way of handling deadlock. Memory management. So we talked about this at the high level. We might get into a little bit of it today, but generally we talked about it at the high level. So the idea of moving applications from the hard drive into memory, ultimately from memory, gets loaded into the process manager, and we have to do that moving stuff back and forth as lines of code are needed, which is driven by the program counter in the current job being run, that kind of stuff. So all instructions have to be in memory in order to execute. That goes back to something we talked about a few minutes ago with the speed of memory. We want instructions to be in a staging area that is quick. So we're not going to load them off of the hard drive. We're going to load them out of system RAM. And then as they're working on the CPU, they're going to be operating out of one of the various caches, or some of the various caches, including registers. Okay. So the memory management activities, they keep track of what's currently in memory. They decide who gets to move in and out of memory when they're told a program was closed. The memory manager frees up that RAM, that kind of stuff. Storage management. Questions I might ask in here maybe deals with some of the different file systems we discussed. We talked about the NT file system. And we also talked about like the Unix file system, the one the Macintosh system uses, some of the limitations of those two. For instance, if you buy a USB hard drive today, large, and it's formatted typically FAT32, not NT. That way it's compatible with both Mac and PC and Linux, whatever. You have a limitation of a 4 gigabyte single file size, which is becoming more and more of a problem today, right? It's not uncommon to download a 4 gigabyte file today. 7 years ago, that was not very common. Our largest files we'd see, were 1 gigabyte or 640 megabytes, CD size things, where now files are getting bigger and we're starting to be inconvenienced by this FAT32 limitation. Let's see. So, the job of the storage management, creating files and directories, manipulating files and directories, mapping stuff into secondary storage. So, copying things from the hard drive onto a floppy disk, stuff like that. So that's the job of the storage management piece of the operating system. Same argument. This is similar to what we dealt with before, just the comparison between storage stuff. Not really important. The actual how things move from one place to another. We want to think more big picture how operating systems are kind of put together. Probably won't ask security questions. Not unimportant, but I don't think that would be a good use of a question. Certainly the idea of distributed computing, we've talked quite a bit about that, where you have one machine versus several machines, and do they share a single CPU, like when we talked about the terminal server in the other room, having dummy terminals that all share a single CPU, and how do the operating systems on those differ from the operating system that's going to run on a single computer? So that type of stuff. Didn't really talk about special purpose systems. Won't ask a question about that. You know, our examples there would be like stuff, you know, the operating systems on our cell phones and things like that, or that run machinery in factories. Well, the operating systems on our cell phones, which we're going to be most familiar with, they've become basically full-fledged operating systems. They're not as special purpose as they used to be. It's kind of the punchline. Let's see. Well, I mean, computing environments, maybe as it relates to the different kinds of operating systems. We talked about it a long time ago, and then we also talked about it more recently, where, you know, the server version of an operating system might have a little bit different mindset on some of its decisions than the consumer version of an operating system, because they're really trying to meet different needs. So depending on the type of environment the operating system needs to work within, we have different situations. Client-server computing, reasonable enough. I've spoken a little bit more about that recently as we were talking about sockets, some. But you know, the idea that we can have one computer here, another computer there, and they're talking to each other somehow. Peer-to-peer computing, I guess similar to that. We have a bunch of machines linked together in some way, and they need to send information back and forth. We had a discussion dealing with, you know, sharing music and that kind of stuff. I probably wouldn't ask real detailed stuff about peer-to-peer or client-server type things. I could see maybe a question about, you know, why a peer-to-peer network like BitTorrent might be preferred over a client-server type environment. Maybe even a question along the lines of, give me an example of something where a client-server environment would be the preferred method, and an example of when a peer-to-peer method might be the preferred method. So, you know, for example, sharing music, video files, things like that. The modern way of doing that tends to be these peer-to-peer networks, so that the labor of moving bits between point A and point B is shared across many connections, as opposed to maxing out a single person's internet connection. Whereas when you're dealing with things that have less traffic, you might deal with a single client server, or for small transactions. You know, you probably wouldn't do authentication through a peer-to-peer network. You would talk directly to Amazon, give them your username and password, and they'd spit back whether you're in or not. Make sense? That doesn't require 4,000 people to, you know, change a light bulb. This kind of just flips into what I just talked about. It's all the same crap. Probably nothing on that. The concept of program execution. So when a job's actually running on the CPU, how does that work? How do we use the program counter to load the next instruction into the registers, and then that maps to a single magic trick on the CPU, that kind of stuff. I suppose the difference between command line interfaces and graphic user interfaces for working with operating systems. Is there a place for command line interfaces today? Most of us are used to graphic user interfaces, but you've seen me in here several times use the terminal for doing certain things, and sometimes it's just more convenient to do it from a text-based environment rather than having to deal with 50 different drop-downs, most of which you don't need. The concept of system calls, especially our favorite, Abe. But just that idea that the operating system has a special API associated with it, where it can respond to certain commands at an operating system level to do something. So system calls are basically method calls or program executions, but they kind of operate with certain permissions, kernel level access. Getting information into system calls, so passing parameters, the specifics of it, not all that important. Just the idea that some system calls require us give it some information. If you're going to create a new file, you need to tell it the file name, that kind of stuff. Do we have is this a good one? I see Abe smirking.
No, it's.
What happened?
Never mind.
Not classroom appropriate? Is that what's happening? That's what's going down. Okay. So this is just examples of some different system calls. So creating, deleting files, obviously those are going to need some parameters. What file do you want to create? What file you want to delete? That kind of stuff. Process control, we're waiting for some amount of time, waiting for an event. Signal an event, this deals with some of the inter-process communication stuff we've talked about more recently. Let's see, device management. We really didn't talk about these specifically other than requesting a device when you go into the wait queue for I/O. Didn't talk about information stuff at all. More recently, we've talked about like creating communication connections through sockets, sending information between processes with message passing or through sockets. I know a couple of you in the last quiz couldn't come up with some of the specific answers, but you said something along the lines that you could technically pull off inter-process communication through sockets. And that's a true statement. Not what I was looking for, but it is true. So in a pinch, if you could set up a socket connection, there's no reason why you couldn't. Sockets are typically, the idea is they go from one computer to another computer over a network. But there's no rule that says you can't open a socket connection between a program on one computer and another program on the same computer. Probably not the most efficient way of doing it, but certainly would work. Okay. Just examples from operating systems. The idea of microkernel-based operating systems, where instead of putting all of the different aspects of the operating system into the kernel, what you do is you only have the most necessary stuff being part of the actual kernel, the actual operating system, and then sitting at an application layer above that, we have some of the components that we typically consider to be part of the operating system. One of the reasons for this is it does have a performance benefit, it does save some space, but there's also some security advantages to this where we can control the communication between certain aspects of the operating system so that the actual microkernel at the center, we're basically saying, okay, that's administrative access. Those things can do whatever they want, then talk to each other without any sort of security permissions. So that's going to happen in one core. But then sitting above that, now we can control communication channels and the security about them. So more of an object-oriented approach to writing operating systems. Virtual machines, benefits of them, how they work, sharing the resources on a single computer, common uses of them. Certainly, I got asked a question about the differences between VMware and Parallels, something like that. I had you look at a couple of different virtual machines in a paper. So I probably wouldn't ask something super specific, but maybe talking about virtual machines from the perspective of consumer use for virtual machines versus maybe server IT side use for virtual machines. So talked more about this in detail. So this is something that came up earlier. The idea of the bootstrap loader during system boot, how it hands off execution to the actual operating system. There's got, otherwise we have a chicken or the egg problem. How do you have an operating system loaded into memory if the operating system is in charge of managing memory? See what I'm saying? So we have to have some very special operating system, super low level, whose only job is to go take this and do this with it and just say go. All right, so that's kind of our bootstrap. Very domain specific operating system that lives on the motherboard. Okay, so ideas of processes. We never really discussed batch systems. We mostly discussed timeshare type things where we have a single operating system trying to make the end user or end users happy that all the applications that are being requested are running at the same time, as opposed to a batch system which just says, here's a giant list of work, go. We'll check on it in a couple of days or something like that. So that's less about real time. The idea of what's in a process, program counter, stack, data section. Okay, so this is just more specifics about the internals of a process. So we even wrote a process data structure in here. And like I said, we won't have a programming component to the exam, but you should understand what goes into that process data structure. What are the parts of it and what do they do? Different process states and what they mean. Just another way of looking at the same thing. Process control block. Why do we need a process control block over and above just the process data structure? What's the process control block used for? Context switching. So switching from a process to a process. How does that work? Who's involved? We context switch one of the guys out before we context switch the other guy in, and why, and all that crap. Okay, again, details about the process scheduler in general. Here's Leia. Did we spell that right?
Mm-hmm.
So certainly Jabba the Hutt versus Princess Leia could definitely make the exam. Yeah, so really understanding how these different, how the CPU scheduler, and the process scheduler all kind of interact. Really, you can throw memory manager down here as well, which we understand at the high level. How these guys all interact to ultimately execute programs. We didn't really talk about the difference of those. So again, more details on context switching. And maybe kind of an element of context switching that I find typically important is that it's expensive. So that should be kind of a expect questions dealing with the balance between the expense of a context switch and the necessity of a context switch. We need them so we can have more than one program run at the same time, but they're really expensive, so we don't want to do them too often. Well, creation of the process by the process manager. Specifically, they're uniquely identified by a process ID, that type of stuff. They ultimately get loaded into a process control block. So that whole, the process of processes. Certainly the fork system call. It's been a long-term theme of ours, I suppose. But specifically processes as they relate to threads. That's a important concept. Okay, then we get into some of our inter-process communication stuff. Shared memory and message passing being our main form of inter-process communication. And some of the reasons for that. Why are we cooperating? So processes can share stuff with each other. We can solve speed up computation, especially when we physically have multiple CPUs. I don't know if convenience makes tons of sense, but that's fine, whatever. How message passing works. The idea of sending and receiving information. So message passing is an example of direct communication between processes as opposed to shared memory, which would be indirect communication. Synchronization in terms of blocking and non-blocking. So if we need to have one process finish before another process can continue, the one process that's working has to block the other one. It's probably going to be done by a signal. So blocking means they can't run simultaneously, so we don't get the benefit of the multiprocessing for that period of time at least. but it's also necessary for solving that particular problem. Sockets communicating between computers on the network, and I know we're out of time. I'm zipping through this pretty good. Concept of remote procedural calls, kind of a layer above sockets, where instead of executing a socket, we could just call features on another thing, and the socket probably gets created under the hood. Concept of pipes. And finally, let me just jump into this guy real quick. Again, more information on threads, why we like them over full processes. Programming for multiple cores, I already talked about that some, but more details dealing with that. User threads versus kernel threads, not overly important, just one has more permissions than the other. The standard thread library is probably not important. Okay. Questions, comments, concerns? So exam 10:10 a.m. on Monday. I will not be here, but I will be here starting Tuesday morning. So if you have questions or anything, you can circle back with me. All right. I will see everybody when I see you.